This video is for section 8.2, solving systems of equations using matrices. So first let's talk about what a matrix is. A matrix is a rectangular array of numbers designated by how many rows and columns there are, and each entry is a number. If we were to look at this first example, we can write the augmented matrix for this system. The augmented matrix first starts with a square bracket, and we write the coefficients of our x's, y's, and z's and what they are equal to as columns. So the first entry in our matrix would be 1 because we have an x as our first term. Our next entry would be a -1 because we have a negative y as our next term. Next entry would be 3, and the final entry would be 4. And we tend to put a vertical bar representing where the equal signs are. Our next row would be 1, 2, -2, and 10. And our third row is 3, -1, 5, and 14. This is the augmented matrix. To solve a system of equations, we're going to use the elementary row operations as shown here on the right. We can do one of three things in a combination of these. We can add a multiple of one row to another. That's what we're going to be using most of the time. We can multiply a row by something, and we can switch two rows. I'll be using this notation to indicate what operation I do between matrix steps. So the first matrix operation, or the first concept that I want to do, is I want to get the values underneath my first entry to be zeros. So I want the 1 in the second row and the 3 in the third row to become zeros. So my first operation that I can do is row 1 minus row 2, and we'll stick that in row 2. I didn't change the first row. The first row stayed the same. But the second row now, I'm going to take row 1 minus row 2, and I'll stick those entries into the second row. So 1 minus 1 gives me 0. -1 minus 2 is -3. 3 minus a -2 gives me 5. And 4 minus 10 is -6. For the third row, I'm going to take 3 times row 1 minus row 3 and store it in row 3. That creates the 0 as the first entry in my third row, because 3 times 1 minus 3 gives me 0. Then I'll take 3 times -1, so that's -3, minus a -1 gives me -2. 3 times 3 minus 5, it's 9 minus 5 is 4. 3 times 4 is 12, minus 14 is -2. Now I want to get this entry, the next diagonal, to be a 1. And there's several different ways you can do it. I could divide by -3, but that might be a little bit cumbersome because I'll get some fractions here. So I'm going to think, how can I make that entry be a positive 1? Well, how about I take minus row 2 and add it to row 3. And I'll stick that in row 2. That minus the row 2 makes that a positive 3, and then when I add it to the -2, I get a positive 1. But also, the zeros that I've already created do not change based on this operation. That's the other key reason why I used this method to get a 1 in the second entry of the second row. It doesn't change the zeros that I've already created. So minus row 2 plus row 3, so negative 5 plus 4 is negative 1. And then we get negative a minus 6, so it's positive 6, minus 2 is positive 4. I'm going to go ahead and rewrite the third row. My next operation I'm going to do is I'm going to take 1/2 times row 3. I'm going to add it to row 2. And I'll stick that into row 3. That will make my negative 2 in the third row a 0. So I'll complete this operation. I didn't change anything else. So I'm keeping rows 1 and row 2 the same. This time row 3 is going to change. So 1/2 of row 3, and I'm going to add it to row 2. Creates a 0 in the first term, a 0 in the second term, then 1/2 of row 3 plus row 2. So 1/2 of 4 gives me 2, minus the 1 gives me 1 as my new entry. Then 1/2 of row 3 would be negative 1, because it's negative 2 times 1/2, negative 1, plus row 2 gives me 3. I'm now ready to solve, because I can rewrite these equations now based on their new coefficients. So if these are the x's, the first column are x's, the second column are y's, and the third column is z, then the third row becomes z equals 3. I now know what my z variable needs to be. The second row is y minus z equals 4. And the first row stayed the same through the whole process, x minus y plus 3z equals 4. And I'll do some back substitutions to solve for the y and the x. So if z equals 3, then y minus 3 equals 4, so y equals 7. And then I'll take these two values and plug it into my original. So x minus 7 plus 3 times 3 equals 4. I get x, that's minus 7 plus 9, so I get x plus 2, that equals 4. So x equals 2. My solution then is 2, 7, 3. The process we just used was called solving a system using Gaussian elimination. Gaussian elimination is where we specifically get the main diagonal to be 1s and everything below it to be 0s. So to solve this system of equations, the first thing we'll do is draw out the augmented matrix, placing the coefficients of each of our variables in its proper place and with what it is equal to on the very right. Now the first thing I want to do is to get the top left number to be a 1. I see that I can easily divide or multiply by 1/4 by row 1 and store that back in row 1. So let's do that. We get 1, 2, negative 1, and positive 1. And nothing else changed. Now I need to get the numbers below the 1 to be 0s. So my first operation, I'll take 3 times row 1 minus row 2. I'll stick that in row 2. And my second operation that I'm going to do is 2 times row 1 plus row 3 and store that in row 3. So again, the first row didn't change. Now I'll do the first operation. 3 times row 1 minus row 2. So 3 times 1 minus 3 is 0. 3 times 2 minus 8 is negative 2. 3 times negative 1 minus 5 is negative 8. And 3 times 1 minus negative 11 gives me 14. Now I'll do the second operation. 2 times row 1 plus row 3, we get 0 in the first entry. We get 2 times 2 plus 1 is 5 for the second. 2 times -1 plus 12 is 10. 2 times 1 minus 17 is -15. Now I need to get the -2 in the second row to be a +1. So I'll take -1/2 times row 2 and stick it back in row 2. Again, nothing else has changed. 1, 2, -1, and 1 for the first row. The second row has changed. So now I have 0, 1, 4, and -7. And the third row did not change. I want to get the 5 in the second row to be a 0, so I'll take 5 times row 2 minus row 3 and stick that in row 3. The first row did not change. The second row did not change. But the third row now has changed. And I get 0 for the first entry, 0 for the second entry. 5 times 4 minus 10 is 10, and 5 times -7 minus -15 is -20. For our final matrix operation, I'm now going to take 1/10 times row 3 and stick it into row 3. The first row did not change. The second row did not change. But now the third row is 0, 0, 1, and -2. So, rebuilding my equations, I get z equals -2. I get y plus 4z equals -7, and x plus 2y minus z equals 1. Doing the back substitution of the z equals -2 into the second equation, we get y plus 4 times -2 equals -7. Y minus 8 equals -7, so y equals 1. I'll now plug those values into the first equation. And I get x plus 2 equals 1. X equals -3 then. So my solution is -3, 1, -2. In this example, we're going to use Gauss-Jordan elimination. Now, adding the Gauss-Jordan elimination means that all of the entries above now are diagonal, are zeros. So we'll start off by writing out the augmented matrix of the system. We'll go through the process like we just did in the previous example, only ending up going a bit further. So the first operations I would like to do is row 1 minus row 2. Stick that in row 2. And row 1 minus row 3 and stick that in row 3. So the first row did not change. 1, 1, 6, 3. The second row did change. If I take and subtract these, I get 0, 0, 3, 0. And if I subtract row 1 and row 3, I get 0, -1, 2, and -4. Here I'm going to switch two rows. I'm going to take row 2 and I'm going to switch it with row 3. First row didn't change. Now my second row becomes 0, -1, 2, -4. And my third row is 0, 0, 3, 0. I'm going to take row 2 and multiply it times -1 and stick it back in row 2. And that keeps my first row the same, 1, 1, 6, 3. 0, 1, negative 2, and 4 is now the second row. And my last row is 0, 0, 3, 0. I'm going to take 1/3 times row 3 and stick it into row 3 to make that 3 become a 1. Nothing else has changed, except we have for the last row 0, 0, 1, 0. Now I'm going to work backwards, and I want to get the 6 and the negative 2 to become zeros, and I'm going to use my third row to do that. So I'm going to take 2 times row 3 and add it to row 2, stick it in row 2, and I'm going to take negative 6 times row 3 and add it to row 1 and stick it in row 1. The reason why I want to do this is that the other entries being 0 don't change anything, except for the 6 to become a 0 and for the negative 2 to become a 0. And now for the final operation, I'm going to take row 1 minus row 2 and stick it back into row 1. And so my final matrix is 1, 0, 0, negative 1, 0, 1, 0, 4, and 0, 0, 1, 0. So that means z equals 0, y equals 4, and x equals negative 1. And that is the solution. Now let's take a look at what other types of solutions you can get. First of all, you can get no solution if every entry except the last is a 0. What this means then is 0 is equal to 1, which is not true, so we have no solution. We get one solution like the previous examples, where we had a number in this last slot, regardless of what the last number is. So we have some sort of coefficient on the z, and it's equal to something. We get one solution this way. We get infinite solutions if the last row is all zeros. So let's take a look at how to write the answer when we have an infinite solution. So the first case, our last row indicates we have 0 equals 0. So that means we're going to let z equal t and have the same case where t is any real number. We'll use the second row, which represents y plus 3z equals 2, and solve for y once we replace the z with a t. So I get y equals negative 3t plus 2. Now I'll use the fact that z equals t and y equals negative 3t plus 2 and plug those into the original first row that we have. So I'll take x minus 2 times negative 3t plus 2 plus 3 times t equals 6. I'll expand all this out, being careful of the signs. Combine everything that I can. X plus 9t equals 10, and x equals negative 9t plus 10. So now I have my expressions for each of the x, y, and z's. So x is equal to negative 9t plus 10. Y is equal to negative 3t plus 2, z is equal to t, and t is any real number. And that is the solution for an infinite system using matrices.